All right, off we go. We are in chapter 3. Chapter 3, there we go. And we are playing with estimating population parameters. And so what does this mean? Well, we're going to go way back to the beginning of the course when we were talking about sampling. So we have this population that we want some information from. And populations are kind of nebulous, like a cloud. And then what we do is we pull from that population some sample. And a sample is very concrete. And then based on that sample, we do calculations, summary statistics. For example, we might pull from that population in the sample a proportion. Proportion is usually abbreviated with a P with a little hat on top. But we might get a mean from the population, or the sample, excuse me. When we make a sample, we hope that sample is representative. Representative of the population. It's like the population in all possible ways. Okay. Now, it isn't the population. Every sample you take is a little bit different. So if later we go and we pull another sample from that population, it's a very concrete set of information. We eventually put it into a spreadsheet. And then based on that spreadsheet, we calculate things like a proportion. Oops. I'm going to call that P hat 2. 2 there. There we go. And we pull again a mean out of that. Call that mean number 2. And that sample is going to be a little bit different, even though we hope it's representative, but it's not going to be the same. So that means it's going to have a slightly different mean, and a slightly different parameter of proportion for whatever we're talking about. Okay. And every time I do this, it's just going to be a little bit different. So we pull another sample out. Sample 3, and from that sample, we calculate a proportion of something on a qualitative variable. That could be proportion 3. And we pull another mean out of that. So a couple of things I was looking up the other day was teens who believe that social media harms people their age. Or the average could be the average body mass index for people. There's another one I was looking up the other day. So percent of teens that believe social media harms people their age, right? That's either they said yes or no to that question. And I calculate the yeses and I get a proportion. Right? The body mass index, we would then have to have the person's height and weight. And based on the height and the weight, we can calculate the body mass index. We calculate that for everybody, we average them out, and then each sample has its own average, right? And you do agree for every sample, we're going to have a slightly different average because they're not the same group of people. But we hope the sample was generated in a random way that's going to make it representative of the population, but they're all going to be a little bit different. So a few things to think about. If we happen to have all of the population information, we could make a histogram of that. So based on the population, we could make a graph of whatever we're measuring and count the people, and maybe the graph looks something like that. And every single sample here, also we can make a histogram for whatever we're measuring. And it's going to look a little bit different. That's going to be more histogram-y. Maybe it's going to look something like this. And everyone's going to look a little bit different. The green one's going to have one too. Maybe it looks more like that one right there. And they're all going to be similar but different. Okay. Now, it turns out we could graph, say I need a different color, how about blue? We could graph, we do a whole bunch of samples, and we just record that proportion for the sample. And then we could make a histogram based on all of these proportions. And it's going to look similar but different. Okay. So I have three kinds of histograms going on here. This one up here would be a population distribution. Right? And all a distribution is a histogram of whatever data we're looking at. In this case, I'm talking about, in a minute, I'll get to the actual data, proportion of teens who think social media is harmful to people their age. Then two here, we have sample distributions. It's different than the population distribution, right? Population, maybe we're talking about teens in the US. Okay, that's going to be tens of millions of teens in the US. The sample is probably going to have like 1,000 to 2,000 people in it, right? Much smaller. That's a single sample. And then let's say I do 100 of those samples of 1,000 teens. 1,000 teens here, 1,000 teens there, 1,000 teens there. Repeat that 100 times. Then I'm going to have 100 proportions to graph down there. Okay. When we graph a selection of sample statistics, that is called a sampling distribution. So this is a third kind of histogram we can make, but they're all histograms. And this is called not a sample, but a sampling. And this is a lot of what chapter 3 is about, the sampling distribution. In this case, it would be a distribution of sample proportions. Sampling distributions is going to be the main topic for the next 4 weeks, at least in this class. And there are many, many, many kinds of sampling distributions. We're only going to focus on 2 of them. One is a distribution of sample proportions. An example of this is with US teens. I'm going to get many samples with, let's say, 1,400 teens in each. So somewhere I find a list of teens in the US. Maybe I get phone numbers or addresses. And there's going to be, say, how many are there going to be? There's like 300 and something million people in the US. Maybe 10% of those are teens. So maybe I'm looking at like 25, 30 million teens I have a list of. And from that list, I'm going to grab randomly 1,400 and then another 1,400 and then another 1,400. I'm going to do that over and over again. And all I calculate from that list is the proportion that said, write that down, proportion of teens that claim social media is harmful to people their age. And I actually did find a study that looked at this. Anybody want to take a wild guess at what the proportion might be? Proportion of teens that say social media is harming other people my age.
40%.
40%, good one. Yeah, someone else.
Let's go with 30.
30%?
Yeah, like 30% is what I was gonna say. I think it's pretty low.
Yeah.
There's definitely gonna be some there, but
Yeah.
don't expect it to be high.
So my guess is if you asked the team, do you know somebody that was like bullied through social media? Every one of them is going to say, yeah, I know somebody that was bullied. Yeah. We'll get to that in a minute. Usually when I don't know something, if I totally have no clue, I just say, 50%. Right? But other times if I'm like, oh, no, I don't think it's 50, then, I might guess lower or high, but 50 is the kind of thing we might guess at for something like this. So again, what am I doing here? This is important, that I get many samples, each of 1,400. 1,400 there, 1,400 here. I do that like 100 times, 1,000 times. Right? Even if I do it 1,000 times, that's still much lower than the actual population of teens. And I only graph, that is histogram, this proportion. And we'll do this in a minute with a computer help. Proportion. That is what a sampling distribution is. It's different than the population distribution. It's different than the distribution of any one of those samples. But it is a very helpful, parentheses goes there. It's a very helpful tool in statistics, and I'll show how we're going to use it today. So there's many kinds of sampling distributions. We're going to focus on two this quarter. One is distributions of sample proportions. And the second one is distributions of sample means. Okay. Example of that would be BMI of US adults. And to create a sample distribution, I would have to collect many samples. So I would then get many samples with, let's say I'm going to choose 1,000 adults for each sample. And then again, I'm only going to graph, that is, make a histogram, the means. So that is, I take a sample of 1,000, I get their height weight, I use that to calculate the BMI, and then I average the BMI. So from that sample of 1,000, there's only one number I want, the average BMI. Then I do another sample of 1,000. And I whittle it down, I compress it to a single number, the average BMI for that sample. And I do that again and again and again, and I plot all of those means. That is a kind of sampling distribution, and it's different from the population distribution. It's different from the distribution on any specific sample. And we're going to experiment that idea in just a minute. Right. And like, I think most people are still having a problem. Like I give you a sample, identifying the population of interest. Sometimes that's a challenge. Getting used to this third kind of distribution can be a little challenging. It takes a while to get used to. But by the end of the term, you'll be used to it. But it's going to be a struggle for a couple of weeks. All right, so let's see. I'm just going to copy some things here. I want that. All right, so from the research, I got this statement right here. 48% of teens say social media harms people their age. And that's up. This study came from in 2023. And I'm going to bring up that study right now. Maybe go So this was from the Pew Research Center, which is a pretty good place that does all kinds of research. Most teens credit social media with feeling more connected to their friends. That's good. Still, roughly 1 in 5 social media sites hurt their mental health. And then further down, it gives that statistic I just quoted here. 48% of teens say social media harm people their age, which is up from 32% in 2022. And then they show some other statistics based on their study. The green line over here. Oh, I must have clicked on the graph and loaded the whole thing. There we go. The green line is that negatively affected their peers. Let's see. That social media is neither positive or negative went down from 45 to 41%, and that social media is mostly positive went from 24% to 11% from 2022 to 2024. How did they collect this data? So there's all kinds of information about how they collected it. If you want to read more, I'll put a link to this in the chat and on the video online, but they have the full report here and then a summary of the report there, in addition to this, media write-up that they have up here. Back to the notes. There we go. So correction, that's not 2023, it was in 2024. All right, sample size. With this particular sample, it was 1,391 teens and parents. Now they had to get parental consent for these surveys. So the teens were interviewed with their parents, ages 13 to 17 for this study.
Responsible.
Yeah, that's a good question. That with the parents there, it might skew it. There's probably more details about exactly how they went about the interviews. I just read the article pretty quick, and again, I've used Pew a lot. They're very reputable. Now, when they make a claim like this, the implication is that this represents all teens in the US. That's the point of doing research like this. We think we have a good representative sample, so we can say, okay, this is what's true for the sample. We believe this is about the same for all teens in the United States, which is the target population here. All samples vary. So another sample, it might be lower. Another sample of 1,400, it might be higher. Okay, it's going to vary from sample to sample a little bit. So we have to take sampling variability in mind. It turns out we can simulate, bless you, that sampling variability. So somebody whip out a calculator for me. I need to know what is 48% of 391, of 1,391. Bless you.
1169.
That sounds too high.
You said 84?
48% of 1,391.
668.
668. Okay, that sounds about right. So we're calculating a proportion. For a sample, it's called a P with a hat over it. Without the hat, it means population. Okay, so P hat means a sample proportion. A proportion is calculated, portion, by counting something. So in this case, we counted up, they said, yes, I think social media harms people my age. And so there were 600 and was it 68, Jonathan? Okay. Yes on that question. Out of the total of 1,391, and that comes out to be approximately 48%. So the way we can kind of simulate variability in the population, variability of samples, is we could make a bunch of cards. So we're going to make a deck of cards. And that deck of cards is going to have 668 yes cards And then let's see, what's the difference there? Calculator. Through 1391 minus 668. Chat up here. Chat people, help me out. Zoom friends, what are you doing? There we go. 723. Thank you, Lex. There. All right. So then there's going to be 723 no cards. Shuffle the deck. Really good. And then what we do is we draw a card. We record what the card said, yes or no. We put the card back in the deck. And then we shuffle it and repeat. And we're going to repeat 1,391 times. What's going to happen is based on those yeses and nos, we're going to get a new set of yeses and nos. There's not going to be 668 of them though, for yes. It's going to be slightly different. Why? Because I put the card back in the deck each time. This technique of draw a card, record it, put it back in the deck, shuffle it, repeat, however big the sample was, this is an idea called bootstrapping. The data. And STAT243 is designed to bootstrap data. So we're going to jump over to STAT243 and we're actually going to do this and see what happens. And STAT243 can do it super fast. It's a very well programmed site. Ready, set. Now I'm going to whip out STAT243. Eventually you're going to need to do that today because we're going to do some hands-on stuff with our computers. STAT243 from our textbook. And we are in the confidence interval section. So last few weeks, we were playing in the descriptive statistics and graphs section. This week, and we're going to play with the bootstrap confidence intervals, and then soon we'll be in the randomization hypothesis tests. And I am doing a CI, confidence interval, for a single proportion. So I got to pick the right one here. And mostly we're just going to either do a proportion or a mean. We will look a little bit at the end of the course at a difference in means, but not yet. So single proportion. And STAT243 has a bunch of preloaded data in there. I'm going to edit their data out and my data in. For a proportion, you just need to know what's the count of the favorable thing and what's the total. So for 48%, we decided based on the calculation that 668 people said yes out of a sample size of 1,391. And then STAT243 off to the side says your original sample had a count of 668 and a sample size of 1391, which gives you a sample proportion of 0.48, which meets my expectations. And then what I'm going to do is I'm going to hit the generate one sample button in the upper left. And what STAT243 does is exactly what I said. It makes a digital deck of cards where there's 668 yes cards and there's what, 723 no cards. And it shuffles that deck virtually. It pulls out a single card at a time, looks at it, puts it back in the deck and just writes it down. So what STAT243 did super quick is it reshuffled and redrew 1,391 cards. This time there were 656 yeses doing that. Okay, and it's because it's putting the card back in the deck each time. If it didn't put the card back in the deck each time, you would get exactly the same sample every time. Okay, so this method reflects variability as if you did a whole new sample of the population, if the first sample is represented. If your first sample is shit, then this whole process is shit. So you got to have a good sample to start with. And I can do it again. So I'm going to, and notice it plots down here. See at the bottom, that point down there is this new bootstrap sample. So I'm going to generate another one. It's a little bit different. This time it's 658 for the count. Another one, 682, a little higher. Another one, 669, a little higher. Right, and notice all these dots forming at the bottom. Each one of these dots on the bottom, if I click on it, it's going to tell me which sample it is up there. Every time I click on a dot, I get a different one over there. I want to do this a lot of times. 10 more, 100 more, 1,000 more. In the book, they often do like 2, 3, up to 6 or 7,000. I think it's a good practice to do at least 6,000 resamples. And again, the computer does this super fast. Okay. If you have an older computer and a bigger data set, it might slow your computer down a little bit because your computer is running this, not the internet. When you go to the STAT243 website and you click a button like the confidence interval for a proportion, it downloads to your laptop a program that makes all these calculations for you. And I have an old laptop that I use, and some days for big data sets, my laptop starts to shake a little bit and get hot. So I want 6,000-ish. Okay, so I now, if you look in the upper right corner of the box, I have 6,115 samples. Each sample consists of 1,391 people. So every single dot, and there's so many dots they're blending together, but I can click on them, and each time I click on one, it's going to update the bootstrap sample over here. I don't really care what each individual one, but what this shows me is if your first sample up here was a good representative sample, this is what variation in the population probably looks like. Is this a distribution for the population? No. Is this a distribution for the sample? No. This is what's called a sampling distribution. It's a distribution of statistics, a single number from each sample of 1,400 people. And I just did how many of them? 6,115. It's saying the average value in this particular graph, so of all the proportions, it turns it into a central proportion. It says that's 0.481. That number there will always be similar to the original one, but not the same. My original proportion was 48%. The average of these 6,000 resamples is 48.1% close. And then it gives me a number called the standard error. The standard error is the standard deviation of this graph right there, which is different than the standard deviation of the population of the sample. All right, so I just want to draw some things on here for you. I need all of that. Current page for that, there is not. So this is a distribution of sample proportions and some things you should point out. So make a sketch on a piece of paper. So write this title, distribution of sample proportions. And then you're going to make a graph in your notes. And then your graph is going to have, I'm just going to outline this. That, let's highlight it to make it more obvious. I'm just going to even out the spikiness. That's my graph. The graph is centered at the middle of the distribution is about 0.481, which is represented up there. And you remember the two standard deviation rule, the 95% rule? 95% of values are between two standard deviations if the distribution is bell-shaped and symmetric. Is this bell-shaped and symmetric? Yeah, I think so. And the standard error here is the standard deviation of these sample proportions. So if I look two standard deviations to the right, let's see if I can calculate that. Let's see, the standard error is 0.013, which would be 1.3%. Two of those would be 2.6%. If we add that on to 48, we've got like 50.6%. So then one standard deviation to the right is over here-ish. Two standard deviations to the right is over here-ish. Going the other way, one standard deviation to the right is going to be about here-ish. Two standard deviations to the right is going to be about here. And so I'm jumping by that 0.013 there. And I'm just guessing at it. I could calculate it later, but I'm pretty sure that's where they're going to land. And what we should find is that 95% of these sample proportions should be in between those two numbers. Okay, so somebody help me out with the calculator. This number on the right is 0.481 plus twice the standard error, which is 0.013. What does that calculation give us? Need a couple people with calculators. Zoom friends, room friends.
507.
Sounds about right. Confirmation from someone? Yep, thank you. And let's do that in the other direction. On this side, that would be 0.481 minus 2 standard deviations or standard errors, 0.013. And that number is about 0.455. Yeah, okay. 0.455. All right, so here's the deal. We have a single sample of about 1,400 teens, and 48% of them said that social media was harmful to people their age. So again, here's the claim. 48% of teens say social media is harmful to others their age. Or I guess they said people their age. Right? Every sample is a little bit different. So what I can say is, well, the actual population one for all teens in the US is probably close to that, but not exactly that. Making a sampling distribution gives me a window of what to expect due to natural variation in samples. And our 2 standard deviation rule says that 95% of other samples will have numbers in this range, proportions in this range. So 95% of other samples will have a proportion somewhere between, on the low end, 45.5%, and on the high end, 50.7%. 95% is a pretty good group of information. I don't have 100%. We never have 100%. It's not possible. Population's too big and squirrely. So 95% is a good target. That's not 95% of teens. That's 95% of similar samples of teens. Each sample has 1,391 teens in it because that's the one I started with. I have to stick with the same sample size. So this is probably a good study. The sample is likely representative of all teens in the United States, but because of sampling variability, the population proportion is probably not exactly 48%, but it's somewhere in that range. More likely, it's between 45.5% and 50.7%, somewhere in there. Could I be wrong on that too? Yeah, I could be wrong on that too. The actual population could be slightly outside of that, but it's probably not going to be too far from that. All right, summary. So again, goal of this chapter is estimating population parameters. So in this case, we're doing proportions is a kind of parameter. Mean is another kind of parameter for a population. So P is, the population proportion. And I don't know what it is. I'm estimating it with the sample proportion. Sample proportion is called p hat. This is also called a point estimate. point estimate because it's a single value estimate. We can also make what's called an interval estimate. Based on stat key, I think the proportion P is between 0.455 and 0.507. I got that using the 2 standard deviation rule. So this is what's called a 95% confidence interval. And so if you look at the fine print of that study I brought up from Pew, what they'll eventually say in the fine print is they'll either state their interval estimate, or they'll state what's called a margin of error, which I want to illustrate next. And we'll take a little break. Confidence interval, margin of error. And I'm going to illustrate that based on the graph we made a minute ago. So we had a histogram of sample proportions that looked kind of like that. In the middle over here was 0.481. And then we measured out 2 standard deviations to the right and got 0.507. And we measured out 2 standard deviations to the left and got 0.455. So from here to here is my confidence interval. In the middle is my point estimate, P hat. Usually the distance from the center to the edge, either on the left or on the right, is the margin of error. Now, because we did this using like shuffling a virtual deck, the interval is not perfectly symmetric. So the number I find on the right is going to be a little bit different than the number I find on the left. I'm just going to double check that in the calculator, and I'll show you the best way to come up with the margin of error for a situation like this. Let's get a Desmos going. Okay, so if I go on the right side, that was 0.507 minus 0.481. That gives me a margin of error of 0.026, which makes sense because we were using the 0.013 before. And then 0.481. Oh, this one's going to be symmetric because of the way we calculated it. That's nice. 0.455. That's going to give me the 0.26. So this one came out good because of the way we set it up, but it's not always going to come up perfect as that. So on either side, I'm getting a 0.026 for the margin of error. To be safe, what I usually do is I find the distance all the way across and then cut it in half, right? So typically when I want to find the margin of error from a situation like this, I'm going to take the high number in the interval, subtract the low number in the interval, that finds how wide the interval is, and then I cut it in half to get the distance from center. So that's the typical way we're going to find margin of error. And you're going to do that a whole bunch this week and next week and some other weeks after that. Now, StatKey will actually do some of this for you up front. So if I go back to my StatKey, so I just looked at the standard error up here and then just added it twice to the right to get a number. But in StatKey, what you can do is click the two tail button over here on the left. And what StatKey will do is it will count up all of the points here and find the bottom 25% of them and make a mark. Go over 95% of the way farther, make a mark. And then there's 25% of samples in the upper end. And so StatKey says not quite the same as what we calculated. It says on the low end, it's 0.455, which is what we calculated. But on the high end, it's getting 0.506. And there will be some variation like that when you use StatKey to do it, because it's literally counting points, as opposed to just applying the standard error, which is slightly rounded. Okay, so if you use the standard error technique like I used a minute ago, you're not necessarily going to get exactly the same answer. Oops, that's StatKey, got it, go away. Why 95%? Well, we've got the two standard deviation rule. That's about 95%. So that's a common thing to pick. But we could say pick a different number in there, and we'll talk about that next class. But most of the time, we're going to go for 95%. So this is what's called a confidence interval based on a sampling distribution. And that has to be done with some kind of program that reshuffles data fast for you. Okay? You can't do this by hand. It would take days and days and days and days and days to try to do this by hand. It's nuts. You wouldn't do that. So until we had powerful computers like we do today, this was a dream method in statistics. So back when I took statistics, this wasn't possible. Computers weren't powerful enough to do that in a day or two. All right, so one last thing about this example, and we'll take a quick break and do another one. So here's what we have about this particular situation. After all that math and explanation, we started off with 48% from that survey, of that research, 48% of teens say that social media is harmful to people their age. The source for this, of course, was Pew Research. And in the fine print in Pew Research, when I read the details, they said the sample size and was 1,391 teens. That means our sample proportion of 48, when we multiplied these two together, we ended up with 668 in the top and 1,391 on the bottom, which gives us about our 0.48 as a decimal. All right. And in this case, we had to calculate that number based on those two. This is again called a point estimate. Is it going to exactly match the population? The answer is no. So that's why we come up with an interval estimate. So then we use StatKey to find a 95% confidence interval. And we can state intervals in math in two ways. We can do like I did back here, where I do a compound inequality, or we could state the interval in parentheses. So I could also state a parentheses 0.455, low value, comma, 0.507 for the high value. If the sample size is big enough, and each of us uses StatKey, again, remember StatKey is like shuffling the deck. There's a lot of randomness there. We're not going to get exactly the same results, but they should be very similar. But if the sample size is large enough, it's going to be pretty damn close almost all the time. And for the population of teens we have here, 1,391 is actually a pretty good sample size. We'll look later at how to get a better sample size. Okay. Based on that confidence interval, we calculated a margin of error. Of 0.026. And at the moment, we have two ways to do that. We could ask StatKey to put 95% in the middle, and then we do a quick arithmetic to figure out that based on the confidence interval. Right. High minus low over 2. Or we could do it with the standard error. So in this case, because I use 95%, then the margin of error is approximately twice the standard error. And the stat key screen said the standard error was 0.013. So we have 2 ways with stat key to come up with the margin of error. We can either use the standard error, or we can have stat key create the interval, and then we do our arithmetic. And we're just going to do that a couple more times with different samples after this to try and get used to that process. If you ever read some statistic like this claiming something for a big population, if you can't find either the confidence interval and the confidence level, or you can't find a margin of error, then their statistic is worthless. You have to back it up with a margin of error or a confidence interval. You can't just have the point. In the news, right, in the newspaper, they're just going to say the point. They're not going to go into the details of how they got about it, but there should be some place where you can look it up. Okay. So this might be like a New York Times article might elaborate on this, and New York Times will reference, they got this data from Pew, and you go to Pew, and Pew says, oh yeah, this is how many people we have, we used a 95% confidence interval, and this is our margin of error. All right, that was a lot. We got a while to get used to it. Let's take a quick break, and then we'll come back and play more with this.
Hey,
Stand
Gary,
up.
I have a question.